Okay, I'd like to introduce our next speaker. Our next speaker is Michael Allen, speaking on fence tiling derived identities involving the metallonacci numbers, squared or cubed.
Thank you. So first of all, thank you very much to the organisers for a really wonderful conference in such a beautiful city. So this is work I'm presenting on behalf of my co-author, Ken Edwards, who couldn't make it. I think I'll call them the metal numbers to make it easier for me to say. Right, so what we're dealing with, again, is N boards. And we're going to tile these N boards with tiles which are made of two pieces, and we're calling these fence tiles. The two pieces are of width W and have a gap of G between them. We're going to have W is equal to 1 over P, and G will be 1 minus 1 over P. So when we tile a N board with these fence tiles and also rectangular tiles, we have to completely tile it. So in the end, there should be no gaps. So an outline. So I start off telling you what I mean by the metallonacci numbers, and then we'll see that a combinatorial interpretation of those numbers is to tile an N board with dominoes, and instead of just one type of square, we're going to have squares of C different colors. And then we're looking at combinatorial interpretations of those metal numbers to some power P, and we'll look at the special cases P equals 2 and P equals 3. So the reason for calling them the metal numbers is because the metallic means or ratios are defined in this way. And we have the famous golden ratio, silver ratio, and so on. Some people call the third one the bonds ratio. We're calling them the metal numbers because if you have this recurrence here where we've got the normal Fibonacci recurrence, but we have a C multiplying the first term, then the limit of the ratio of successive terms is the metallic ratio. For we've got C equals 1, it's the golden ratio, and so on. So these numbers seem to be of interest. I gauge that because if you look at the OEIS for the first 20, they're all there. They have a few interesting properties. The fourth one in the series is actually a half of the even Fibonacci numbers. The 11th one is a fifth of F5N, and it turns out that the Lucas P metal number is actually given by this nice simple expression. So they seem to have sort of quite interesting properties. So tiling an N board with dominoes and C types of square, as Art was explaining, we can get to recursion rate relation like this. We basically condition on the final tile. If the final tile is a square, there's C types of square, and then we just need to tile the rest of the board, which is a length n minus 1. If the final tile is a domino, there's only one type of domino, and we've got n minus 2 cells left to tile. Little m, I'm calling the number of tilings of an N board. It's an offset from what we defined as the metallonacci numbers by 1. So how about a combinatorial interpretation of the metal numbers to some power P? Well, the obvious way to do it is to consider P N boards and you tile them independently. But another way of doing it, if you actually only want to tile one board, then what you can do is you can think of shrinking these 3 boards by a factor of P, in this case 3, and then you alternately select. So this red one goes to the first, what I call slot of the first cell. The pink one goes from the second board, goes to the second slot, and the first half of the domino goes to the last slot here. Then you see the next one, the green one goes to the first slot, the grey one goes to the middle slot, and this one goes to this slot here. So we end up sort of slicing and chopping up things, and this is how we actually naturally get fences. So we end up with an alternative tiling interpretation of the metal numbers to the power P, which is the number of ways to tile an N board using 1 over P by 1 rectangles, which I call R, and these fences, which have a gap. So the key to counting things using when we're tiling with fences and rectangles is that any tiling with an end board can be represented as a tiling of using meta tiles. And now meta tile is a collection of tiles which covers an integer number, a whole number of cells with no gaps. And another property is that a meta tile is minimal in the sense you can't split it into more than one meta tile. So the simplest meta tile is simply 3 rectangles next to each other. That will cover 1 square. Another simple one is you've got 3 interlocking fences. So here's the first, second, third, like that. And we call all other types of meta tile, this is an example for people's 3, we call those mixed meta tiles, and they'll have some significance a bit later. So we now look at the people's 2 case, which will give us ways of getting identities for the meta numbers squared. Now, in this case, the possible meta tiles are relatively simple. We've got r squared and f squared, but we've also, the other possibilities actually end up forming quite nice, neat families. The thing to notice is that we always have an r at the beginning and an r at the end of these mixed meta tiles. So this is something to remember. And we've got 2 meta tiles of each length. But if we then allow for the fact that r has 2 different colors, c different colors, that gives us 2c squared. So we've got 2c squared mixed meta tiles of each length from 2 onwards. So what can we do with this? Well, if we condition so we let Bn be the number of ways to tile an end board using R and F when p equals 2, and we condition on the last meta tile. Just so this one here is corresponds to this meta tile here, the R squared meta tile, and then we've got F squared, which is length 2, which gives us 1 here, and we've also got mixed meta tiles 2c squared in number, and then we sum over all the other lengths of meta tiles. So this immediately gives us, from the fact that Bn counts the meta numbers squared, this immediately gives us this identity here for meta numbers. And if we take this and subtract the version with n changed to n minus 1, then we get this version here without the sum. So you can produce lots of identities by the various tricks in Art Benjamin's book. I've just selected a few which seem to be a little more interesting. This is actually based on a fairly recent paper by Art Benjamin and friends, which works quite well in this case. So this is the identity we want to prove. And when we prove identities, combinatorially, what we do, as in Art Benjamin's talk, is ask a question and then answer it in 2 ways, and then put the 2 answers, make the 2 answers equal to one another. So how many tilings of an end board contain at least 2 rectangular tiles, 2 Rs? So the first answer, the simple answer, is all the tilings do except the all bifence tiling. Okay, so just review what I mean by bifence. So bifence is the F squared. So all tilings will contain at least 2 Rs, because all of the meta tiles except for the bifence contain at least 2 Rs. So that's an easy question to answer. It's going to be all of the tilings Bn minus, there'll just be 1 tiling if n mod 2 is 0. So if n is an even number, then we can have the all bifence tiling. If n is not an even number, then we don't have that. So the second answer is that we condition on the location of a second R in the tiling. Now, the symbolic representation, so now we'll actually think of our tiling as a symbolic representation. So this is actually what I've been writing on top here. All of these meta tiles end with R in their symbolic representation. And it turns out that you can actually end up with your tiling to have any sequence of F and R as long as it ends with an R. So that makes life easy with counting. So if the K cell has a second R, the symbolic, so this is our K cell here, the symbolic representation of the tiling of the first K cells will have its R here and will end in R, and then we've got K minus 1 Fs plus 1 R that can be placed anywhere along here. They can be, the symbolic representation can have any order we like. So that gives us K ways in which this can be done, and we multiply by C squared because we've got 2 rectangles which can be in any color. Okay, so that gives us the C squared K ways, and then we sum over all possible K. And I forgot, so we worked out how many ways we can tile this, and then this can be anything, so that leaves us with Bn minus K ways to tile that. So we multiply those two together and sum over all K, and then make this answer equal to answer 1, and we get the identity 4. Now, when we go to the P equals 3 case, life gets a bit more difficult. There's no nice pattern to the meta tiles. So we have to have a different strategy, which is we actually look at the ending of the meta tile, and you can see what I've done. We're representing the final cell of a meta tile by its contents. 0 means it's got an R in, and a 1 means that final slot of the final cell has part of a fence in it. And these effectively are, so we're now going to be counting the number of mixed tiles of a given length L with a given final slot on sigma. And you can see, for example, that when we've got 0, 0, and 1, the number of those will be C to the 4, because we've got 2 here, R squared, and we've got another 2 here, R squared. So that's 4 rectangles, each of which can be colored C ways. That gives us C to the 4, and so on. So what we do is actually get a recursion relation for this view L. So we can construct a meta tile of length L from a meta tile of length L minus 1 if we take one of these R's in the final cell and replace it by a fence, the start of a fence. This will sort of link us to the next one. So for example, this F3, if we take the final cell here, okay, let's take this, sorry, no, it's not example. So if I start with R3, so if I take one of those rectangles and replace it by a fence. So for example, if I replace the final rectangle by a fence and then fill the rest with rectangles, I'll get the 0, 0, 1 case. Okay, so we can actually build up the next length mixed meta tile from the previous one. So I won't go into details, but we can just get recursion relations and use symmetry to finally end up with a formula for the number of meta tiles for a given length. And this looks familiar. It's basically our metal number formula, but instead of the metal numbers, the C metal numbers, we have the 2 C metal numbers, and they're displaced by a little bit, and also multiplied by C squared times C squared plus 1. So our final formula is that the number of mixed meta tiles of given length is given by this expression here. So we can then go on to do something similar to before. We can condition on the final meta tile, and here we're summing over all mixed meta tiles, and here we're summing. So we do similar things to what we did with the P equals 2 case. Then using the fact that Bn is equal to Mn plus 1 cubed, we end up with this relation. Subtracting this relation from n change to n minus 1 gives us a more compact formula for the metal numbers cubed. So at the risk of, okay, so this is my final identity. it's rather a pretty identity. What we're aiming to prove is this one here, that the product of these three metal numbers, consecutive metal numbers, is, is this sum here. So to do this, we need a lemma, which is if the number of rectangular tiles in the final cell is Q, then there's this many ways to tile the M board in total. And to prove it, we consider our bijection again. So for each cell slot containing an R, there corresponds an M board tiled with dominoes and squares that ends in a square. But if the final slot contains a post, that's one half of the fence, then that corresponds to a tiling which ends in a domino, and therefore there'll be. So remember, this MN corresponds to little m, m plus 1. Sorry, I got that wrong. So mn is offset by 1. So you normally think, oh, if it's a square, you should have n minus 1, but it's offset by 1, so I have to add 1. Okay. So in the domino gives us mn minus 1. So to prove this identity, our question is how many tilings of an end board end with a right post of a fence preceded by an R? And the answer using this lemma is, well, there's two ways of doing it. It ends with a right post and is preceded by an R. So that leaves one slot left. So we could either have that second slot filled with a half a fence, the post, which will give us a factor of C from the R, and then this thing squared, because we're going to have two dominoes and one square in the bijective tiling, or we're going to have two R's, which gives us this, and one F. And if we use this expression here and add things, then we end up with this result here. Now this is particularly nice if we actually put some values in for C. So if we put C equals 1, which is just, this will then give us the Fibonacci numbers, then we get the product of those three consecutive Fibonacci numbers are. So this, yeah, okay, almost finished. So this will give us with M2 is are the Pell numbers. So we end up with three Fibonacci, consecutive Fibonacci numbers multiplied together, give us this sum involving Pell numbers and the Fibonacci numbers cubed. And then because of this property that if we put C equals 2, remember we have M2C here, we'll get M4 here. Because M4 is actually half the even Fibonacci numbers, then we end up with this sort of dual formula, which if you have the product of three Pell numbers, then you get that as a sum of the Pell numbers cubed times the even Fibonacci numbers. So just a few references. So my co-author was the first person to come up with this idea of fences, and that's his first paper. This work is actually a generalization of our two previous talks, one on Fibonacci numbers squared and one on Fibonacci numbers cubed. And of course, for more details on combinatorial proof, of course, refer you to Art Benjamin's book. So thank you very much.
Are there any questions for our speaker?
Always hard to have questions.